Hello everybody, welcome back to the next lesson. So in today's lesson we're going to be exploring the Doric Capital. We had a look at the Tuscan capital as described by James Gibbs, and we're now going to be looking at his design for the Doric Capital. I'm also going to teach you some alternate designs for the Doric Capital as well, because the Gibbsian Doric is not the only version. There's quite a few different versions of this particular capital, just like there are of the Ionic capital and the Corinthian capital. But again, James Gibbs is our very good friend because he divides everything into fractions, which kind of makes exploring this kind of architecture easy for us. The only downside, though, is how much construction is involved when dividing things into equal parts. And so in this lesson, rather than kind of using his method, we're going to diverge a little bit, and I'm going to show you my method for basically coming to the same result. So, as you're well aware, if you look at this Doric capital, he's divided everything into fractions again, where the height of the capital is divided into 3 equal parts, and the width between the center and the inner column is divided in half, and then he duplicates that half onto the edge to find the width of the abacus, essentially. And he basically continues in this fashion. You can see this middle third here is divided into 3 equal parts, and then the lower third is divided into 3 equal parts again. He does the same on the abacus as well. He divides the top third in half, and then the top half into 3 equal parts. On the edge of the abacus, you can see he divides it into quarters. The third quarter is divided into quarters again, and the end quarter is divided into 6 equal parts. So you can kind of see, like, it works. I mean, we're getting the proportions we need, but you can kind of see how exhausting it is. And if you have a proportional divider, which is such a valuable tool for this way of working, then you're not going to have much trouble doing this. But if you don't have that tool, then either you're going to have to use construction boxes and divide them that way, which it works, but it means that your page can get very messy with all of the construction lines all over it. Or you're going to have to measure some of these parts, find what the distances are, and then use your calculator or whatever to divide them into the fractions that you need. So, Gibbs's way of working it definitely works, but it can get tedious. And you can see how much more complicated the Doric capital is compared to the Tuscan capital. So rather than copying just his method, we'll definitely use his design because it's great to learn from his designs. He is a great teacher. Centuries later, we're still learning from him. But I'm going to show you an alternative, which is basically my way of thinking. So, this is the Gibbsian Doric, and all of his proportions are here. The only thing I've not listed was dividing the very edge into 6 equal parts. This part was divided into quarters. The proportions are there, like I've done it correctly, I just haven't labeled it. But it doesn't really matter because we're going to work a different way anyway. You'll notice I've got this kind of, don't know what that is. Don't need that. I've got this geometric overlay on top of it. And this is kind of how I think about architecture. I don't want to be given just a set of measurements. Unless I have to reproduce something exactly perfectly, then okay, fine, I'll have to look at the exact proportions. But the artist side of me kind of wants to explore the geometry behind the design. And I do this for 2 reasons. Because, well, the first reason is when the ancient Greeks and the Arabic architects and the Roman architects were designing their buildings, they used geometry to do it. They were, sacred geometry was huge in their world. And if you research this topic, sacred geometry in classical architecture, you'll see it a lot. So they used it as a tool to design the buildings. And so I like to explore these designs and see where the geometry kind of fits. The second reason is if you can learn to think this way, yes, it might take you a while to explore the geometry behind the design, but once you know it, you can potentially work a lot faster. Now, when I'm going to demonstrate this to you, I'm going to work quite slowly because I'm going to try my best to think about all the things you need to be doing, and I'm going to try my best to explain it to you while I work through it, right? So I'm not going to be working quickly today, but you can potentially work very quickly when using geometry for your designs. The third reason, actually, there's a third reason. When you think geometrically and you try to explore the geometry behind these designs, it teaches you to think more creatively when you're working on your own designs. So you can take what you've learned here, and then if you want to design your own capital or your own whatever it may be, a doorway or a piece of furniture, then you can kind of think back to how we use geometry to construct this capital, and you can do the same thing for your own designs that way. So this is kind of what I want to teach you. Like, I don't want you just copying fractions and proportions like so many people do. I want you to actually explore the hidden design behind it, let's say. And I'm not saying this bit of geometry that I've whipped up is the design for the capital. I'm not saying that's how this was made. But what I am saying is that these are some of my own findings, and this is what I found, and this is what I found works. And you can get very creative when you think this way. So let's dive right in. So the first thing you're going to want to do is you're going to want to create your central axis that runs to the center of the page. You always do that. You always do that. My computer just froze for some reason. Oh, no, we're on. Okay. There we go. So start with your vertical axis. Find out where that one's going to go. What I'll do, I'll place the height at exactly the same level as my previous drawings, because then we can compare the measurements. So somewhere on that vertical axis, you're going to mark the top of the capital, wherever you want to put it. Obviously, it's going to sit somewhere along the top of the page. I don't think you want to put it at the bottom, because I don't think that's going to be great for you compositionally. Now, what you have to do, now, we're only drawing the capital in today's lesson. We're not drawing the base. We'll look at that later. But we are going to need the width of the base in order to construct the capital. Now, you can construct the capital without the base of the column, because these are all modular proportions, so you don't need the full picture. You can work without one part, but you do kind of need the width of the base really in order to set the height of the capital, and you also need it for one more reason. So again, you don't have to use it, but it's very helpful. So we'll take the width of the base, which you're going to be using your compass to do this, and I will simply copy and paste it onto our own drawing, so I've got the exact measure, because again, I want to compare this. But basically, you'll be centering your compass on, let's call this point 0. Right, the OBS decided to stop recording for some reason. Not sure why, but anyway, we're back. So the center of that arc is point 0, since that's the center of the column. And either side of that arc, we've got points A and B. and A and B represent the distance of the width of the base, right? Now what you have to do, you are going to be using Thales' theorem for this part. So go ahead on either side, construct Thales' theorem, and you're going to be dividing that line into 6 equal parts, okay? So you can use your compass to do this, placing notches on the line. 4, 5, 6 measures. And then from point 5, inscribe a line parallel to the last line we just drew. And there we go. So I'll delete these lines since I don't want them getting in the way there. They're just a temporary construction. And again, if you want to check if this distance fits into the width 6 times, just use your compass to do that. Just inscribe an arc from that point to this point. Inscribe another circle. Just keep inscribing circles that cross through each other. You can see where this last circle hits tangent with point O. We go 1, 2, 3, 4, 5, 6 equal spaces. So we've done it correctly. Very quick way to check. I suppose you could measure it with your ruler on the paper, and well, you could measure the distance between 0 and point B with your ruler, and then divide it into 6 equal parts with your calculator, and then see if the measurement you've got here is correct. But I think it's faster with a compass. Okay. So then what you got to do is you need to then use your compass, center the needle on point 0, and inscribe an arc from point number 5. So let me, with small numbers here, I'll put this as point 5. This will be point 6 near point B there, right? So we know that's 6 equal bases, and we're going from point 5. So we get our compass from point 0 to point 5, and that is the width of the upper column, which we're also going to need. And I'll check that with my diagram over here. I'll copy this arc, place it on here, make sure we're doing it correctly. There you go. Looking good. So we're on the right track. Now, in Gibbs's diagram, he wanted you to divide the height of the outer arc into 3 equal spaces, as you can see here on these proportions here, right? What you can do instead is you can actually center your compass on where the vertical line crosses the inner arc, extend it to the outer arc, and that gets you your measure. See where that circle hits tangent? So basically what's happening here is the distances between the inner and the outer column are already giving you that proportion. So there's no need to use construction boxes. There's no need to use calculators. You can just use the geometry that's already there. All right? So we got, let's call this one, go away. I'm so sick of that. So let's call this one point C down at the bottom, right? You're going to point C, and you're going to inscribe an arc to point D right here. So I'll place that there. Oops. Right. Alright, so grab your compass, needle on point C, take it to point D. There's your measure. Alright. And what you do is you repeat that pattern. So you center your needle on the top tangent of that circle where it hits the vertical axis, and you just continue duplicating that pattern until you hit the top. And if you've done it correctly, this last circle will be tangent with the top. So it's really cool when you figure out how geometry works and how it gives you these measurements. It's all about paying attention to the design. So this first circle, the top of that circle, which I'll label what should I call that one? Well, let's call it point E, right? May as well just keep using the alphabet. So we've got point E, which is going to represent 1/3 of the height. So we'll drag that across. Also, make sure you extend a horizontal line from the bottom, from point D there. And well, that's quite easy to see. I was going to label it, but I don't think we need a label for this one. But you can see there, 3 equal parts. And if you wanted to measure that, I've got a number of 11, 6, 7 there. It's all equal. So it's just much quicker to do it that way because these arcs are giving you that proportion. So it's all about using the geometry that's already there. And so if you go back to the Gibbs's diagram, he tells you to divide the top third in half, which again, these circles are already doing. So let's label that point F. All right. And we're going to need point F for something else as well, which is why I'm labeling that one. So we got that, which is cool. But you could have also found that a different way. So let me take you to the edge of the inner column where it hits the top there. That's tangent. If I just dropped a line onto point D, and then let's say I centered my compass on point D and bring it out to that line from the edge of the inner column, that gives me point F. Could also just use your set square and draw a 45-degree diagonal from that corner to point F to find that on the center axis, which then gives you that top half of the abacus, right? So that's why geometry is such a wonderful tool if you know how to use it. So we got the top of the capital, we got the bottom, not including the astragal, but we're going to get there. And we've divided that abacus in half with point F, right? So it might help if I label these. So this is, let me use a bigger one. Abacus. This curvature here is the ovular, don't know how to pronounce that one. This is the astragal here. I'm not very good at pronouncing these names. I don't know how to pronounce it, but I do know how to draw it. And that's what I'm teaching you. So some people call this the necking, the bit between the ovolo and the astragal. Honestly, it doesn't matter. It doesn't matter how to. We don't have to label everything. As long as you've got those 3 main elements there, then you're good. But we'll carry on. Right. So the next part we have to do is we have to divide the distance between point A and point 0 in half. Actually, no, my mistake. I've not labeled it on here. Let me call this one point. Oh, Jesus, there's going to be a lot of points. I'm going to call it X. Actually, you know what? I'm going to call it 0.1. That's what I'll call that. Just as long as we got some kind of note on it. So 0.1 to 0.0, divide in half. So you just draw a 45 degree, which you can see meets point C. So then if you describe a horizontal line from point C to the line of 0.1, the vertical line I should say, and then you just, that will, if you draw a 45 degree angle from that point, that takes you back to 0.0. So that's a square box that we just constructed. And the center of that box will divide that measure in half, right? And then you will center your compass on point, let's call this one, hang on. We'll call this 2. You know what? It would make more sense if we flip those numbers around. Let's make this let's make this 1.1. Right. Now, so from point 2 to point 1, inscribe an arc. Okay? And then where that arc takes you is the edge of the abacus, as can be seen on the diagram here. And we're going to label that 1.3, which makes sense. So at this point, I'm going to highlight this line with a dark line. I'm going to draw a line from point 3 to point 0. So that's the distance from the edge of the abacus to the center. And I'm just going to draw on this half of the drawing and then I'll duplicate it. And you can duplicate it with your compass. Remember that technique. So any measurement can be transferred horizontally onto the other side of the vertical axis, right? Now, Gibbs is telling us to divide that into 3 equal parts, as you can see here. So I think you can just go ahead and do that. I'm just wondering if I figured out a different way to kind of doesn't look like it. So, well, let's come back to our drawing. So let's create a little construction box on this quadrant of the circle, on the top circle here, so we can just, because we've already got a 45 degree down there, we can just cross another one through it going in the opposite direction, and then take that to 0.0 there. That's 1/3. Take that across, and then we can just drop a line from point 3 down to that horizontal Drawing that back up there. There you go. Ooh. It's not quite perfect. There we go. So we got that part. Now, you need to divide the distance between point 2 and point 3 in half. So we can get that part in there while we're still working in this area. That's halfway. And then you got to divide it in half again. So just go from this point, from this vertical line you just constructed. It's in half again. See that? I'm probably not going to label those points because I don't think it's quite necessary to do that. I think we'll live without labeling those. But what you will need to do, where you just divided it last time, just draw a vertical line that drops straight through, like so. And you can see how that, hang on, I'll draw it on this diagram so we can see it better. That creates the lower edge of the abacus, right? So that will connect up to that line, which, if I dimension this, let's put those 3 equal parts in so we can see it a bit better. You take it to the bottom part of the top third of the height, and that will create the lower portion of the abacus. So we can just go ahead and draw that in, really. Always refer back to your diagrams to make sure that you're doing it properly. Because that's the thing, you can't remember all of this. It's too much. But it's not about memory. It's not about memorizing a method. It's about being able to read a diagram, whether it's proportions or measurements or even geometry. It's all about looking at a diagram and knowing how it's made. So it's all about reading a diagram. That's what it's about. Okay, so let's go back to that quarter here, which I will label 0.4, I guess. You're going to just draw a circle, centering your needle on 0.4 and describing an arc to 0.3, like so. And I'm going to show you why that is. Let's go back to the diagram. So, if you looked at Gibbs's diagram, he tells you to divide this last little piece into 6 equal parts to get the measurement for this curvature, right? Because you can see there's a slight bevel in the edge here. It might be clearer on the other side. There's a bevel here, there's a bit of a bevel there. And he tells you to get those measurements, you must divide into 6 equal parts. But you can see very clearly that if you were to inscribe a circle that we just did, and where it crosses the horizontal line there's an intersection. And it finds you those points. And then all you got to do to transfer the point from this corner to the lower corner, you just use your compass, or you could just measure it with your ruler and just transfer it onto this part. And then you've got it. You've got the point that you need. So, very useful technique to know that. So what I'm going to do, got my intersection there. So I'll go from this corner and inscribe an arc till it crosses that circle on that horizontal line. And then using your compass, keep the radius and just transfer the needle of the compass onto this part of the abacus, right there. And that's the measure that you want. From this point to this point is going to be the construction that you need. So that's pretty cool. So let's go ahead, because I think we may as well complete the abacus since we've almost finished it. So you need to find the perpendicular bisector of this line, which you can use with your 45-degree set square, like align it with this line and do it that way if you want to. Otherwise, you could go from the extremities, from point to point, and where those circles intersect is that perpendicular bisector. You could probably just measure it by eye, since I'm sure on your page it's going to be a very, very small measurement, so I don't think you really have to measure this unless you want to be pinpoint precise, which is why I'm showing you this. But normally I would just measure it by eye. I'm not going to measure small details like that. It's really no point. So that's your halfway point. And using a similar technique from this side to that side there, and from this corner, you'll inscribe an arc like this. So we already drew this construction on the Tuscan column. So you should get a curvature like that. So let me remove those circles and we can do it on the other side. I'm just going to delete some of my construction lines because I want to keep the drawing clean. Then from this point, because we're looking for this part of the S-bend, over here. There you go. Pretty cool. And I'll just extend that across to meet the S-bend there. So there you go. That's the abacus completed. Pretty easy. And again, when you practice this enough times, you can do this very, very quickly. So let's go back to this diagonal line. If you draw a diagonal from the top corner and it intersects with the edge of that circle, you can carry that down and you can find the bottom corner of the abacus there, which we've actually already got. So I'm going to delete that line. So that's another way you can find that proportion. So I'll just draw a line there. You can see how that diagonal, it's a bit off in this drawing, but it's very close. And when you zoom out, it intersects anyway, so probably not too inaccurate. But you're going to want to continue that line straight down. Just go all the way down. It's always good to extend your construction lines because, you know, when you're working with geometry, you don't know if it's going to meet anything else, basically. But where that line hits the bottom of the height, which we already have, as can be seen on point D, that actually gives you this interesting construction where we found the radius of the edge of this curve, and we found the proportion of the edge of the... We basically found the edge of the astragal. Alright? So, very useful. So what we have to do then is we need a construction line from this point. Let's just start with a vertical construction line. And we'll extend it both ways, up and down, like so. How many points we got on the page? We've got A, B, C, D, E, F. Let's call this point G, shall we? Point G. All right. So we've got point G. And all we've got to do from point G, have a look at the width of the inner column. Just extend that down slightly because you need to do that anyway. Just inscribe a 45-degree diagonal line from point G till it hits the inner column. And that is going to be one part of your astragal. It's going to be the top portion, that curvature, which you can see this part here, right? That's what we're building. See the geometry in that. So you should be able to fit a perfect circle in that box since it's made up of 45-degree lines. So you can center your compass on the X and make sure your compass hits tangent. And you may need an extra construction line, maybe a horizontal line to help you do that properly. And then with that center horizontal, your compass of the same radius, just go from the edge of that box and draw to the center of it. And that's the curve that you need to complete that shape. So I'll indicate that with a line. So I'm kind of just drawing the forms in as we go so that you can visualize this a bit better. Because to do the drawing just with construction lines, which you can do, but sometimes it's easier to fill it in as you go. Anyway, so now you can see how that form is constructed, right? And then what you got to do from this point is just go from the center of that circle you just drew, project a 45-degree angle traveling downwards, and that's the height of the lower portion of the astragal, right? So and the edge of this box lines with the center of the outer circle, like that. And you just take that back to the center. There you go. Constructed. Easy. Now, I wonder if I've got it drawn in here. I do. So, what Gibbs told us to do in his diagram was from the edge of that box that we just drew, we need to project another 45-degree diagonal. And then that creates this square box. And then we have to divide the height into 5 equal parts. And then we duplicate one of those parts, which would make it 6 equal parts, right? And then you find the curvature of that form. I think that's quite a lot of work to do. Again, when you're drafting manually, I think it's better to find shortcuts if you can. What I found on this geometric diagram, it's the exact same diagram because I literally just copied and pasted this, so that's how you know this geometry is correct. And you can see I've got Thales' theorem in there anyway for demonstration. But have a look at the Vesica Pisces, right, where those circles cross each other, the top portion. If you draw from the top of where those circles intersect and you cut through the center bottom of the first circle and you continue that line, you get the height you're looking for. So instead of doing this Thales' theorem or calculating what that measurement needs to be, just do that. Because again, when you draw with geometry, the construction's already in there, which is why I love it so much. So it might feel like a slug to begin with. Again, I'm working a lot more slowly than I normally would because I'm trying to walk you through it. But when you get good at this, you can work really quickly. And all you got to do then is from the bottom edge here, from the bottom corner to that diagonal that you just inscribed, you'll then draw 2 arcs crossing each other, like so. And that gets the curvature that you need right there. Right. So that's complete. So we still need to finish off the rest of the column, and there's not that much work left to do at this point. So what we will do, let's just draw the neck of the column because there's no divisions on this third here. We can literally just draw it straight up. We can fill that information in. So we've got thin lines, put it there, take it to point E since that's the measurement we want. So that's the neck. And now we've just got to draw the ovolo, I don't know how you're going to pronounce that however you want. Just draw that thing. I'm going to show you how to do it. So, bit complicated. Again, he wants you to divide it. So this middle third, basically, you divide it into 3 equal parts. And then that lower portion you divide into an additional 3 equal parts. And that should get you the measurement that you're looking for. So I don't know if I've come up with any geometric alternative to this. Oh, yes, I have. Yep, this diagonal. Awesome. So how easy is that? Literally just go from the corner of the lower abacus to the inside column, right? That top of the bottom third right there. Horizontal with point E. That's the construction we need. And have a look at the radius of this curvature that we drew previously, and you draw a vertical line from that radius, and where it hits that diagonal, I believe is where we need it. Yeah, that's right. So, and then what you can do, well, I'll draw this in for visualization purposes. This is kind of what I do for this part. Now, I will admit, this I'm kind of deviating from Gibbs's plans here because it's not quite accurate, but it still gets you 99.9% there. I just take a shortcut and I do that. So I'll redo that for you. Go away. 45° from that bottom corner of that construction box. Take your radius, your compass, and that basically hits tangent with that diagonal that travels from the abacus to where we are. And that gets you that curvature bit, this lip right here, right? Now, admittedly, that's not quite true. So if I extend this across, that lines up. If I was to extend this line across just for... oh, that actually lines up too. Oh, okay. Maybe it is right. I'm just comparing my plans here because I thought it was slightly... No, that's lining up perfectly. Okay, maybe it's correct. Cool. Great. Let me go from the sketch that we're constructing. Yep. Yeah, that's looking good. All right, well, just do it like that because that's correct. I did it, I practiced it some other time and I didn't quite get it lining up, but that just means I did something wrong. Let me check this part. This part. Yeah. There you go. Yeah, not quite. But when you zoom out, I mean, that's already zoomed into the drawing well enough, and this is like the full drawing. So, you know what I mean? It's close. That is very close. It's off by like 1 pixel. So I would go ahead and just use that method, honestly. I honestly don't think it's quicker, it's easier, because what Gibbs wanted you to do was he wanted you to divide this section into thirds, which means you could do that easily. I mean, you know how to do that. But using this existing diagonal and then this 45° to create the radius is just so much quicker. And it's 99.99% accurate. So you know what? It depends how much of a perfectionist you want to be. If you want to do it the proper way, you can look at James Gibbs's diagrams for that, or you can do it my way, which is pretty much going to get the same results anyway. Now, we've got to construct this curve. This is the last part of the drawing, and I'm trying to remember. Didn't I have? Oh, yeah, that's right. So again, this kind of comes back to, if you have a look at his diagram, there's a bunch of tiny measurements above the abacus, which is how you find the position of this curve, basically. I found something pretty interesting. So we have to travel back to the abacus. Now have a look at this tiny circle here, right? And what you're going to do from that tiny circle, go to the center of it, and using a set square, draw a 45-degree diagonal line, right? And then from the top of that circle, draw another diagonal. You can see it intersects with this larger circle here that we used for the S-curve. So you'll be able to see where you're going with this. But just draw a diagonal that travels to that 45 degree where it hits that lower quadrant of the circle there, right? That's going to be the radius for your new circle, which we'll inscribe here. Because again, I found a quicker way of getting this measurement on the page. And where this circle you've just constructed crosses that horizontal line, which I'll mark with this construction line here, that's the position of where that overload begins, that curvature. So, from that point then, you'll create a bisector with your compass. So center the needle on that point and take it to this corner here, and then reverse it. Do the exact same thing. And you'll find that angle right there. And where those arcs cross, that will be the radius you need to construct that curvature. So if you didn't quite get that, just watch that part of the video over again so you do understand it. See, there's bloody circles everywhere now. But you can see in the diagram I've got next to it, you can kind of see where that is. Oh, no, sorry, I did it wrong. Oh, bloody hell. Disregard. All right. Got it wrong. Got it wrong. Don't shoot me. Get rid of the circle. Right. Let's do it all over again. I'll start from scratch. That was my mistake. Right. So you got that line, that vertical line that you constructed. Take it to there, that top corner of that lip. Bring it back. All right. And now, I've already got this line in there because I forgot to delete it, but that's correct, right? So that's your bisector that you need. Now, where that diagonal line is, look at where it crosses the bottom of the abacus, that horizontal line. That's the radius you need. So I'm going to create an additional construction line that takes us to there. And that's the part that you need to construct the proper curve. And you can see that it lines up with our previous construction line and it lines up with this corner here. So that's how you know it's correct. Like that. And you can see how that curvature, if you continue it, it goes, it's not quite tangent with that horizontal line, which is correct. You don't want that to be tangent. So that's what you want. It's marked on the diagram next to it. See these dashed lines here where they cross over? See where that curves through there. I'll just shorten that. And that one there. So you should be able to figure that one out quite nicely. There you go, guys. You've done it, or at least you've done one half of it if you're working on one half of the drawing. But again, I already showed you in a previous lesson how to transfer measurements with your compass. So you can just go ahead and do that to mirror it. Because I'm doing it on the computer, I can just press a button and do it that way. But anyway, you can finish off the drawing like that. So I hope you enjoyed that one. That was a bit of a lengthy one. You can get it done quicker than that, but I need to take my time to walk you through it because there's a lot going on. But I want you to really practice with geometry like that because it might not be the most efficient way. I think it's pretty efficient for myself. I can get that done pretty quickly if on the drawing board. But, you know, there might be more efficient ways to draw that capital, but I find that exploring geometric design is very good for your creativity. And you're going to find this especially useful when you're working on some of your own creations. Let's say you wanted to take this capital and you wanted to change something about it. Maybe it's a proportion or a size. You could use the geometry that's in there and play around with that. Because human beings are naturally attracted to geometry, right? That's why it's such an important tool. I mean, we have the ability for pattern recognition. So that's why geometry is such an attractive art form. And it's in classical architecture. It's everywhere. It is everywhere. You have to search for it a little bit, but it is there. So get practicing with that. If you didn't like my method, then you can always refer to James Gibbs's diagrams for that. Again, it's available on archive.org. So James Gibbs rules for proportion, yada yada yada. It's a long title, but anyway. There's another Doric Capital which I'm going to introduce you to. I think you're going to like that one. And it's a bit more simpler to do with... You still use geometry for it, but it's way simpler than this design, so I think you're going to like that one. But play around with that. Geometry is a lot of fun. It's a really fun tool. You can get extremely creative with it. So, and you know what? Go to, this blank drawing here. I'll provide you with this template as well. And maybe try and see if you can find any other geometric patterns in there. Because the thing about geometry is there's always more than one way to get to the same result. It can be a bit of a rabbit hole, and there's a whole world of it in there for you. So maybe see what other patterns you can find in there, because they're in there. That's just how I do it. And it works very well for me. But you might find something much, much better. So have a play. See what you can find. This is the thing about this course. I'm encouraging you to be creative with this stuff. I don't want you to just copy what I do. I'm trying to teach you how to think and explore, because that's what art is all about.